Kelly, if you're watching, I'm buying you a sliding compound miter saw from Home Depot. That's what you're getting for Valentine's Day. All right, here we go. Are you ready? All right, here we go. Yep, we're going to skip it, but we're going to write this down, okay? Remember, so this is where we need to kind of connect what Larissa is saying. She says, I can do it, but I don't know exactly why I'm doing it. And she's the one saying it, but the fact is that there's 10 more of you who feel the same way. So let's figure out why we are doing what we're doing, okay? Remember, when we want to evaluate the right-hand sum of the 4 rectangles, you use this formula. You took the width times the sum of the heights. Right? You guys are used to that, right? So do you remember how you found the width? I took b minus a and divided by n. So b minus a divided by n, that is, well, hold on. I know what you're saying. That is the same as these two things. Dx and delta x. Sum of the heights, what you did, if you remember, you took the function, right? And then you plug in, your certain number into the function in order to get the heights, and then you add them all up, right? So I'll put a plus sign here. Plus sign, plus sign. Well, we replace that with these two things. This is kind of the idea of the sum of the heights. That integral sign, which is kind of the same thing as that. So we're just using new notation. And so the formula, again, that we need to remember is this. The integral means the area ascribed underneath the curve of the function dx. So I'll pause while you write it down. Got it? Dx is a really small amount of change. So dx is like your width. Okay? And then the integral of f of x, that's like the sum of the heights. So width times the sum of the heights. That's equal to, we don't actually know how to evaluate that. I'll teach you how to do the integral. That's our shortcut. I'll teach you how to do this next week. Right now what we know how to do is we know that that's equal to the limit as n goes to what? Infinity of the sum from I equals 1. So we start with the first rectangle. How many rectangles do we add up? We go through n. And we allow n to approach infinity. Okay? That's the number of rectangles. We need to evaluate what part of the rectangles. 2 parts. We need to evaluate the height, which is f of x sub I. And then what other part do we need? The width. And the width is delta x. So when I look at this, I see the width times the sum of the heights. Do you see it? Width, sum of the heights. Width, sum of the heights. That's what we're doing. And this whole limit thing, we just do an infinite number of them. So let's do it. That's our function, 2x minus 1/2 x squared. Oh boy. We're going to go from 0 to 4. So, what is the width? I take b minus a, and I divide it by the number of rectangles. How many rectangles? N rectangles. So, I have 4 over n is the number of rectangles. I'm sorry, 4 over n is the width of each rectangle. So I have my delta x. That's the part I got. Now all I need is this f of x sub I. So I just need to know what to put for x sub I. X sub I is the x value at which we evaluate the height and the sum. So that's the number we plug in. So if we start here, this is our starting point. What's our starting point in this problem? 0. And we add on to that. What do we add on for the first one? The width. So we go over one width, and that's where we evaluate the first height. See? We go over one width, and we draw our height. And then we'll go over how many widths? 2 widths, and we'll draw the height. Then we'll go over 3 widths and draw the height. So instead of doing 1, 2, and 3, we do I number of widths. So I number of widths. And what's the width? 4 over n. Because see, it says the sum starts at I equals 1. So we'll do the first width, and then we'll do the second width, then 3 widths, then 4 widths, then 5 widths, and that will allow us to evaluate our heights at the right spot. So what is 0 plus I times 4 over n? 4I over n. So we've got our width, and we have our x values. Express the area as a definite integral and as a limit of a Riemann sum. The Riemann sum is the sum piece. Riemann was a mathematician, and he really helped develop, some of these ideas. Yeah, it's actually a sigma sum. Looks like an E. So the Greeks, just pause. Greeks had, so if an S came in the middle of a letter, it looked like that. Or it came in the middle of a word, it looked like that. If it came at the end of a word, it looked like that. If it was a capital S, which they didn't have capital letters in Greek for quite some time, then it looked like that. That was your capital S in Greek. So 2 lowercases and 1 uppercase. So they use that S for sum. This S is reserved for standard deviation. Okay, now you know. Okay, definite integral from 0 to 4 of two x minus 1/2 x squared dx. So the sum of the heights times the width is equal to limit as, and it goes infinity, of sum from the first width of the rectangle to n of f of 4I over n times 4 over n. No, because you still be, that's your first width. You'll always move one width away from your starting point, so it will always start with I equals 1. And so we plug this 4I over n into what? Ugh. Well, yesterday we did the easy problems. Today we get to look at something more fun. So we've got this 4 over n. We know that this is going to have to be distributed through, right? So let's write that 4 over n times, and then I plug in 4I over n. So what's 2 times 4I over n? 8I over n minus, now I got to take 4I over n and square it. 16I squared over n squared, then times 1/2. 8I squared over n squared. That's what we got. What do you think? Yep, let's distribute the for n. If I do that, I get 32I over n squared, right? Minus 32I squared over n to the third. You good with that? Okay. So what's different about this problem compared to the ones we did yesterday? We got two of them, so you just break it up into two sums. So we just do the first one, and we subtract the second one. That's it. So when it says factor, leaving expression with only I, what we do is we'll take the limit as n goes to infinity of (32 over n squared) times the sum from I equals 1 to n of I. Ask. Because so I factored out the 32 over n squared because I'm plugging in values for I. So the only thing I want over there is an I. That's all I want over there. Minus, now I take out a 32 over n to the third times the sum I equals 1 to n of what? I squared. Right here. I want, are you okay with this one? I can't leave anything there but an I. So I got it factor out the 32 n to the third. So I just pull it apart. I just rewrite this as 32 over n to the third times I squared over 1. I just rewrite it like that. That's all I do. Okay. Oh, yeah, if you weren't here yesterday, this could be a little confusing. Yep. Yep. And it's okay. You guys are doing really good. Trust me. Trust me. So so here we go. So now we've got these two pieces. We know how to evaluate limits as n goes to infinity. We've done that before, haven't we? But we just want n. We don't want i's. So we need to use our substitution pieces. So Sarah and Keely, can you show these two the substitution pieces? Okay, so then they could see where we got those. We did that earlier in the year in math induction. So now I've got 32 over n squared. And we said if we sum up the first n number of integers, it comes out to be what? N times n plus 1 over 2. Good. Minus 32 over n to the third times what? What do the first squareds add up to? N times 2n plus 1 times n plus 1 all over 6. Oh boy. I haven't worked this problem out ahead of time, so hopefully to make it, it'd be so easy to make an algebraic mistake, wouldn't it? No. So yep. Now it's just algebra, right? With a little limit. So What do you notice? What can we cancel? This n will cancel with one of those ends, and this n will cancel with one of those ends. So, let's do the top. Oh, 32 over 2. I like that. So, I end up with 16 times n, which is plus 16 all over n. Minus I guess we could reduce 32 over 6 to... Okay, and now we got to FOIL this out. 2n times n. 2n squared times 16. Or 2n squared. 2n times 1 is 2n. 1 times n is n. Add them together, you get 3n times 16. 48n. And then you get 1 times 1 is, times 16 is, and all that is over 3n squared. So calculus says that we can evaluate the limit of, we can have subtraction, it's okay. All we do is we just deal with this one, and we do that one. We don't have to combine the fractions. We don't have to do that. So let's just combine the fraction. I'm sorry, let's just do them separately. We don't want to combine the fractions. No. All right, so what do you want to take out of the top? N. And you get 16 plus 16 over n. And on the bottom you have n. Minus n squared, 32, plus 48 over, plus 16 over, all over n squared times 3. And it doesn't, like, just a little euphoria come to your brain right at this point where, like, yes, now I can do it. What happens? N's cancel, n squareds cancel. What else happens? 0, 0, 0. 16 minus 32 over 3. And because I like to have nice exact answers, it'll be 48 over 3 minus 32 over 3 is... is 5.3 repeating. And so, I have no idea if we did that right. So, what should we do? Check our calculator. Go Gadget calculator. It doesn't like to work on the smartboard. I don't know why. It is? You did it? Okay, Sarah Savakul said she did it and she got it right, so we're not going to waste time, go back and check. So we got it. Everybody knows how to check it, right? Oh, you don't? Okay, what's our function? 2x minus 0.5x squared. And then if you just go to calculate, which one do you grab? Yeah, doesn't that symbol look familiar now? So we grab number 7, and it draws the graph. You can see from 0 to 4, our lower limit was 0, our upper limit was 4. Booyah! What's up? Yeah, I'll teach you why. You had a question earlier. You said don't necessarily know why we're doing what we're doing. Does the beginning make a little bit more sense? A little bit. Sum of the heights times the width. That's the whole idea. Whole idea. Whole idea. You sure can. We're gonna do one more. Yep, that's all right. What? What? Can you handle this one? Can you handle it? What's different about this? Oh, it's big time. Big time. We got a constant and we started to. Oh, no. Oh, the pain. The agony. We laugh. We laugh at calculus now. Archimedes. All right, let's do it. So, we're going from 2 to 5. 2 to 5. How do I figure out the width of n rectangles? What do I do? Very good. 5 minus 2 divided by n. So, you moron. 3 over n. A lot of algebra in this one. This one gets nasty. We got 3 over n. Notice our problem is not the calculus. Our problem is the algebra. That's what it comes down to. Everybody get why we got 3 over n for the width. Okay, then for what x values do you evaluate the sum? Do we start evaluating at 0? No, we start at 2, and after 2 we move over one width. Plus, what is the width? 3 over n, and so each time we're going to move over that many widths. Okay? So if the width is 1, our first spot would be 2, because we started 2, and then we add that first width. So you can just see it right here. Look at this spot. You know? Let's say that width is 1/2, and that spot is 3. You can see that the first spot you evaluate will be 3.5. And then your next spot will be 3.5 plus a half. It'll be 2 of the widths that you'll move over to 4. And so that's what this does for you. It generates, those points at which you evaluate the heights. So, we got it. This is 2 plus 3I over n. Express the area as a definite integral. What is a definite integral? 2 to 5. Whoop. 4, what is it? Plus 2x, 1fx squared. Ick. God, why do I pick that problem? Okay, so that's the definite integral. We're going to express the definite integral now as a Riemann sum. Sum from I equals 1. I is the number of rectangles that we start with. So we're going from I equals 1 to n of my function evaluated at 2 plus 3I over n times 3 over n. So, yep, we're going to do that. So sum of the heights times the width. That's what we're doing. And how many rectangles do we want to add up? About infinity. So we take the limit as n goes to infinity because you can't really plug in infinity. If we could just do this and add up, 20 of them then, see what we get. But we want to do an infinite number. This gets kind of messy. Can I go to a bigger space so we can work this out? All right. So I can't really use that guy right there because I'm already out of space over here. So I've got the limit now as n goes to infinity of the sum from I equals 1 to n. Now we got to plug in 2 plus 3I over n and multiply the entire thing by 3 over n. So I got 3 over n is going to multiply everything that I plug in. So can you plug it anywhere to 4? No. So I just got 4 plus okay, good point. Okay, so let's pause because a lot of stuff going on here. So we're going to take this right here and we're going to plug it into our function. Okay? So I'm going to write it all out. So Larry, what you said, I'm going to dismiss that for a second. So I've got 4. That's that 4 plus, and then we're going to multiply this through by 2. And if I multiply through by 2, I get 4 plus 6I over n. I'm going to write in parentheses just so you know where that came from. Minus 1/2 times. What do I do now? I gotta square that. Ugh. Let's do it. Okay, good. 4 plus. Now we gotta take 2 times 6, or 2 times 3i over n is 6i over n, and then you double it. 12i over n. Now we got to square the back. What's 3i over n quantity squared? 9i squared over n squared. So we're not really substituting a known sum yet. We're doing a lot of other stuff. Okay. I feel good about it. Do you? Let's do it. We're still on D. We're still on D. Okay, we should probably just distribute, shouldn't we? All right, limit as n goes to infinity of the sum from I equals 1 to n of 3 over n. And we've got 4 plus 4 plus 6i over n minus 2 minus 6i over n limit as n goes infinity of the sum from I equals 1 to n. Okay, we can combine some pieces here. We got 4 plus 4 is minus 2 times 3 over n, 18 over n. Good. Oh, the 6 i's cancel. Oh, isn't that beautiful? All right, I didn't even see that till now. I was so. A lot of times I see it ahead of time, so you don't see my genuine excitement. That was genuine right there. All right. Minus. Oh, whoop! We got to multiply through by 3 over n over n to the third. Okay. Ooh! What? Oh, you got the 2 on the bottom. Thank you. I would have been done. Done. I would have been redoing the problem because we would have, Okay, so now we just got 2 parts. So now we just do 2 of them, right? So now we're doing part E. Oh, hello! Welcome back! All right! Woohoo! Woohoo! Aslan! Aslan! I'm Guru! You are my minion!
Your legs are
Is that crossing the line? A student saying a teacher's legs are too thick? Oh. Well. Was that a fat joke? Because I just need to know. I need to go on a diet. Okay, I got it. All right. All right. I agree. They're super wonderful people. Let's not allow them to distract us from what's really important. Okay. let us factor out everything that doesn't have an I. Factor out an 18 over n. Sum of I equals 1 to n. When you factor out 18 over n, what do you have left? 1. Minus, now let's do the next one. Factor out a times the sum of, or from I equals 1 to n of I squared. Okay, so if I add up the number 1 twice, what will I get? If I add up the number 1 5 times, what do I get? If I add up the number 1 n times, what do I get? So remember, our first rule was, if you end up with a constant, you just take that constant times n. Okay. So now we have the limit as n goes to infinity of 18 over n times n. It cancels. Minus 27 over 2 n to the third times. Go ahead, Larry. Very nice. Okay, what cancels? Come on. Ends. And this end cancels one of those ends, leaves you just a n squared. Hello! Yay! Limit as n goes to infinity of, what do we have left? We got 18 minus little Billy. She's back. You're right. Good. We're almost there. We can leave the 18 alone. Because the limit as n approaches infinity of 18 is, this is a constant function. Always has a height of 18. What do I factor out at top? N squared times 54 plus 81 over n plus 27 over. Well, what goes away? And 81 over n and 27 over n squared go to. So we get 18 minus 54 twelfths. 18 27 over 6 divided by 3, so 9 over 2. So what I've got now is I got 36 over 2 minus 9 over 2 is 27 over 2, which is 13.5, which is what Zach said. Well, we checked on the... Zach cheated, checked it on the calculator ahead of time. Now, we have to admit, our hearts do go out to those who were not here yesterday, right? I mean, come on. The first time you saw it, you were like, what? In fact, if I recall, you even asked, we're not actually going to have to do this, right? This won't be on the test, will it? But now you can do it, can't you? So those who missed yesterday, they're going to need a little bit of time. Tomorrow we have a work day. You're ready to try some problems, aren't you? Okay. Like 1 or 2? Let me pause the video. So great job today. These 4 problems, and you have all day tomorrow to work on them in class. We got about 25-minute classes tomorrow, okay? So it's going to be pretty quick. So you definitely want to get started. Good luck. You're doing a great job.